Okay, we're
All right. Bio 100 DL1. This week we will be covering the urinary system, the kidney and its functions. I guess to begin, we need to make the statement and make sure that we understand that the functional unit, we have two kidneys, okay? A couple of important points. The kidneys, in their location, they are located, the kidneys, and you may see this question pop up somewhere, but they are located retroperitoneal. Which is to say that they are not within the peritoneal cavity, okay? For most people, the right kidney will hang a few centimeters below the left kidney, and the functional unit of the kidney will identify as the nephron. And each kidney contains about 1 million of these, give or take one or two. Okay, and these are the units where blood is filtered and where substances that are necessary to maintain homeostasis are reabsorbed back into the blood and or secreted into the tubular fluid, which eventually becomes urine, and depending upon the existing conditions of the body. All right, located retroperitoneal, and that's important, so I have to put a little asterisk by that. And approximately 1 million of these functional units, these nephrons per kidney. Okay. The most important part about this, we don't need to, well, we do, I guess, some of the general structures of the kidney. Okay, and we're going through, and we have what they call the renal sinus. And again, a sinus is just a, I guess, big opening into an area called the hilum. And if you look at a kidney, just like kidney beans are shaped, they sort of have, and then there's an indented area called the hilum. And this is the area where blood vessels and nerves enter and exit the kidney. Okay, the large portion of the kidney where fluid collects is the renal pelvis. And this is where, if we look at the diagram on page 525, diagram figure 17.2, you'll see that the renal pelvis is the large area where by the time it reaches into there, will be called urine, will collect and then move into the ureters, okay? So in the urinary system, we have the kidneys, some structures, renal pelvis, you have a renal cortex, just like with any organ, and you have a medulla. Okay, and most of these so-called nephrons, these functional units of the kidney, most nephrons are cortical. In other words, they are located in the cortex, and many of them will extend down into the medulla. So most nephrons are cortical. And then we'll get into the structure of the nephron, which is really the meat and potatoes of the kidneys, what they do, and what we need to know about them. Okay, so you have the major structures made of pelvis, the cortex, you have calyces, again, collecting areas, okay, and then there's pyramids and renal pyramids. All right, so these are just basic structures. What you need to do is just kind of look those over there. You know, we're not going to get real picky about dissecting these particular areas. Just be aware that these structures are there, and you know, when urine is formed, comes through the calyces or the pyramids down to the calyces, and then to the pelvis, and then from the pelvis they'll go into the ureters. We have 2 ureters. All right, and these ureters will empty into the urinary bladder. All right, now, I suppose, you know, a lot of people have an idea about what the kidneys do. They say they filter the blood. Well, yes, they do that, but our kidneys are designed to, a primary function is to concentrate urine and conserve water. And in the urine, we want to get rid of waste. So functions are, you know, concentrate urine, some of the, you know, primary functions. Concentrate urine, conserve water. They also aid in regulating blood pressure. And they also secrete a hormone that is involved in hematopoiesis, and that's red blood cell formation. That particular hormone is erythropoietin, P-O-I-T-I-N. Okay, so these are some of the primary functions of the kidneys. Concentrate the urine, and if you think about that and try to put it in perspective, you're asleep overnight, you're not doing any activity, and your kidneys are, you know, about 25% of your total blood flow throughout a given 24-hour period goes to the kidneys. Flows in through these functional units called nephrons, and they will remove waste and certain toxins if they're present, and conserve water and concentrate the urine. And you can remember this by usually the first void in the morning, the first time you go to the bathroom in the morning, it's very yellow, very dark colored, and may even have an odor to it. Okay, and that's because your kidneys have been busy, if you will, all night concentrating your urine and conserving water. So that which comes out as urine is filled with waste products that we don't need. Okay, I'm not going to belabor the particular structure, but we want to take a basic look at the kidney, and we'll start off with, you know, coming down off the descending aorta into the abdominal pelvic cavity. We'll look at the blood flow. And blood flows into the kidneys via 2 large arteries called the renal arteries. Okay, and then these arteries will branch out and they'll go into the arcuate arteries and into the interlobular artery, or into the interlobular and then the arcuate arteries, the corticoradial arteries, and the final branch, the one that we're going to pay most attention to. So we have from the renal arteries into the interlobular or lobular arteries. Because you may be asked to identify the direction of blood flow and what it's going through. And then we have the arcuate, and the arteries, and then the cortical radial arteries. And this is actually, just for identification purposes, to put them in a particular sequence. And then from the cortical radial arteries, we get into the arteries that we're concerned with, and that we're concerned with all of it, but the sort of the meat part of this. And this is the afferent arteriole. Okay, now we're going to get into the nephron and its structure. Okay, so the blood flows from the renal arteries, the major arteries off the aorta, comes in, and then we get into this afferent arteriole. All right, and this is where we actually start to begin the process of urine formation. Okay, so from the afferent arterioles, we move into a structure called the glomerulus. And these are capillary-like blood vessels, a tuft of capillary-like blood vessels, where the filtration process takes place. Capillary-like vessels, and then filtration takes place here. Now these glomeruli, for plural, are located within a structure known as the glomerular capsule, or I guess Bowman was the guy, Bowman's capsule. So what happens is the blood comes into the afferent arteriole. It enters into the glomerulus, and this is part of the nephron, these capillary-like blood vessels. And because of the hydrostatic pressure in the blood, okay, because of our blood pressure, fluid and dissolved substances are pushed out or filtered through these glomeruli into this area called Bowman's capsule. I think your text may refer to it as the glomerular capsule.
Is it true that people with chronic high blood pressure can have kidney damage?
Oh, yeah. High blood pressure can do a lot of damage to these rather delicate structures. Now, these capillaries are kind of, they're similar to the capillaries, in the systemic circulation. However, they have, they're highly adapted for the process of filtration. So they have these so-called, fenestrations, or holes, if you will, that allow a large volume of fluid and dissolved substances to pass through. Certain larger substances like certain plasma proteins, they're too big, they can't fit through these holes. Okay, but filtration takes place due to the blood hydrostatic pressure. Okay, so in other words, when the blood comes in through this afferent arteriole and enters into this Bowman's capsule, the pressure in these capillaries is greater than the pressure that's in the capsule itself. So blood and dissolved substances are forced out. Water and dissolved substances are pushed out by blood hydrostatic pressure, because it's higher in the blood than it is in the capsule. Now, things that are not generally filtered or removed from the blood during this process are red blood cells, formed elements, and larger plasma proteins. But things like water, salts, sodium and chloride and phosphates and certain magnesium ions, all of these things, they're filtered out and they collect in this Bowman's capsule, okay? And they will, what's left of them after the other processes of urine formation are completed, some of them will be retained and remain in the urine and be expelled from the body. Many of them that the body needs will be reabsorbed back into the blood, all right? I'm going to try to keep this as simple as I can. So we've entered in through the afferent arteriole, gone into the capsule. Because the blood hydrostatic pressure in the glomerulus is higher than in the capsule itself, water and dissolved substances are forced out, okay? And then they collect in this capsule, and then from this capsule you will have, well, I guess before I do that, and then the blood will leave this glomerulus after all this stuff has been pushed out and the other stuff remains, like cells and larger plasma proteins. They'll enter into what's called the efferent arteriole. Okay? Now, we have, in these kidneys, they're just marvels of engineering in their design. You come out of the efferent arteriole, and if you look on page 528, figure 17.6, you can see where, and I guess if you look at this as we go through it, it'll make it a lot easier, but from this efferent arteriole, this will branch out into another system of capillaries called the peritubular capillaries. And this is where substances will be reabsorbed, things that the body needs, and things will be secreted into the peritubular capillaries. And as the name suggests, peritubular, peri means surrounding or around, and what they surround is the kidney tubules.
You say branch into?
Yeah, they branch. Okay. This efferent arteriole will branch into these peritubular capillaries that surround the kidney tubules, and I'll identify those tubules. All right, and I'm just going to kind of put it up over here. So the first process in urine formation is filtration, glomerular filtration. All right, so we'll just, and then as we continue to go through this, I'll add the second and the third. The first is glomerular filtration. All right, and again, that happens because of blood hydrostatic pressure. You know, it's similar when we were talking about the cardiovascular system. Materials seem to move out of arterioles in the systemic circulation out there into the into interstitial fluid, because the blood pressure at the arterial end of a capillary bed is higher than it is at the venous end of a capillary bed. So materials move out at the arterial end, and then they'll move back in at the venous end, because hydrostatic pressure is greater at the arterial end and blood colloidal osmotic pressure is greater at the venous end, so it tends to pull materials back in. And the blood colloidal osmotic pressure is provided for by primarily these large plasma proteins that are not filtered. They stay in the blood. Okay. First step in urine formation is filtration. Okay. And just as an aside, I guess I should say that on average, for the average adult, the GFR, the glomerular filtration rate, in the average person is about 125 milliliters per minute. All right, so we're squeezing out this stuff, this water and dissolved substances at a rate of about 125 milliliters per minute. All right.
Is a milliliter a cc?
Yes.
Okay.
They're equivalent, yes. Now, if you do the math, and you do 125 milliliters per minute times 60 minutes an hour times 24 hours a day, it equals into about 180 liters of this fluid being filtered per day. Okay, now obviously we don't put out 180 liters of urine per day. Because remember, this stuff is filtered. It goes into Bowman's capsule, and then it's going to start traveling through the tubular system. I got to get this out of here. I'm going to keep it. So then the question remains then, well, what happens to the bulk of that fluid then? And the bulk of it, we will see in a second, is reabsorbed back into the blood. Because again, the kidneys are designed to conserve water. We can't live without water. We got to have as much water as we can possibly retain. All right, so we have this first step filtered at about 125 mils per minute, approximately 180 liters per day. Now, after at this point, when all of this stuff, when this filtration takes place and the fluid enters the Bowman's capsule, okay, and then we said then the blood will leave. Now we're going to talk about, and now we're at this point. The blood is in, the filtered material, which at this point is called filtrate. It is not called urine yet. And this filtrate is water and we'll say dissolved materials from the blood. Filtrate is in Bowman's capsule. That portion of the blood which has not been filtered, we just said, will enter the afferent arteriole, which then subsequently will branch into the peritubular capillaries which surround the tubules, which we'll address right now. Now, this filtrate from Bowman's capsule will enter into a series of tubes. All right, so that filtrate will enter in the first tube closest to the glomerulus is called the proximal, because it's closest to the point of origin. That's what proximal means. The proximal, convoluted, because it's all twisted and what have you, tubule. T-U-B-U-L-E. All right, now, and you have to remember these peritubular capillaries that branch off the efferent arteriole surround not only this proximal convoluted tubule, but the other, so that we'll identify in a minute, where this filtrate is flowing through. So let's try to keep this straight. The blood has come in through the afferent arteriole. The filtration process has happened. Water and dissolved substances have entered into this structure called Bowman's capsule. The remainder of the blood goes out of the glomerulus into this efferent arteriole, which then will branch into this capillary system that surrounds the kidney tubules. So now, to filtrate at this point, that which is in Bowman's capsule starts to travel through this tubular system. Convoluted tubule. Okay. It's at this point where we start to reabsorb back into the blood those materials that the body needs, primarily water, sugar, glucose, salts, sodium, potassium, chloride, magnesium, things like, and different ions. All right, so in the proximal convoluted tubule, we start a process called tubular reabsorption. All right, that will be step 2 in this urine formation. We have tubular reabsorption. All right, so now all of this water and stuff that was squeezed out of the blood and began its journey through this tubular system, beginning with the proximal convoluted tubule, materials are being reabsorbed. In the proximal convoluted tubule, if you'll see, it'll tell you the things that are primarily, you'll need to just check, put a little asterisk by those materials that are primarily absorbed in the proximal convoluted tubule. One of them.
And where is that in the book?
I'm going to try to find that here.
Just a list. Oh, here it is, table 17.1.
Yeah. Well, you have the relative concentration of substances in the plasma, in the filtrate, and in the urine. So we're looking in the filtrate. Let's look at under filtrate. You'll see that in the filtrate, there's about 142 milliequivalents per liter. Potassium, calcium. This is what's in the stuff that's traveling through the tubes. All right, sugar. Potassium, calcium, magnesium, chloride, bicarbonate, sulfate, phosphate, and so forth. Glucose, urea, and uric acid. Now these are byproducts. Urea is a byproduct of amino acid metabolism. Amino acids make up proteins, and uric acid is a byproduct of nucleic acid metabolism. Anyway, you can see that the amounts in the plasma and the amounts in the filtrate are equal, but then when we get to how much of that actually ends up into the urine, what doesn't end up into the urine, of course, is reabsorbed. And the important one down there, look at glucose.
100, 100, 0.
0. So normally, there is no sugar in the urine. Now these tubules, not only the proximal, well, let me go through those and then we'll talk about some of those substances. From the proximal convoluted tubule, it goes into a structure called the loop of Henle. Henle being the fellow that, or what do they call it? They call it the nephron loop. Different textbooks will call it something different, but the nephron loop. So you can imagine that this fluid now is traveling down this tube. It's left the proximal convoluted tubule. Things have been reabsorbed. Okay, it's traveling down this tube. There is a series of capillaries that also surrounds this tube, and different materials are reabsorbed depending upon the state of
Is this nephron loop as long as it appears to be in the graph?
No.
Now what I meant though is it's proportionally long.
Proportionally long, yeah. And this, a lot of the times, most of these cortical, because if you look and you see, the cortex is the outer region of any
that's
organ.
17.3.
Yeah, and so most of these nephrons are located in this cortical region, but these loops, these nephron loops, many of them will extend down into the medulla. And then the conditions there, the amount of sodium, the amount of chloride, the amount of bicarbonate, hydrogen, ions, and things like that, the amount there will dictate which substances will move from this filtrate back into the blood and which substances will move from the blood back into the filtrate to eventually be removed from the body. Okay, so we've
Why
got...
do we need two kidneys?
Why do we need two? Actually, you can live with one. Two is just to be efficient.
Okay.
Okay? All right, so this filtrate has traveled to the proximal convoluted tubule, the loop of Henle, and then I'll just identify the third, the distal convoluted tubule. And I won't go through because it would take too long to go through what substances are reabsorbed or secreted where. But from this distal convoluted tubule, it will go into what's called a collecting duct. Okay, and if you look and see, I'll show you where the collecting duct, yeah. And then from the collecting duct, the material will then enter into the renal pelvis broadly. And then at that point, well, after it goes through these pyramids and these calyces, it will end up in the renal pelvis. And then from the renal pelvis, it will go into the ureter. We have two from each kidney.
The collecting duct's on figure 17-13, 17.13.
Yes. And they will, you can see the collecting duct going down. All right, in that particular diagram, you see the proximal, the loop, the distal, and then the collecting duct. And then these collecting ducts will end up dumping urine into...
And what figure is that, please?
This is figure 17.3.
Okay.
And they will dump the filtrate at this point into the pyramids, which terminate in the calyces, which then eventually terminates into the renal pelvis. And then from the renal pelvis, and that's a larger collecting area, into the ureters, both right and left. And then from the ureters, it goes into the urinary bladder. But a third process that I haven't mentioned yet, but we will kind of recap this. So the blood has gone into the afferent arteriole. It's been filtered. The filtration takes place. That water and dissolved substance enters into Bowman's capsule. The remaining blood leaves Bowman's capsule via the efferent arteriole, which then branches into these peritubular capillaries surrounding the kidney tubules, and then that will eventually become those peritubular capillaries will become larger vessels like venules, and then the renal veins. And then the renal veins will come out of the kidney through this hilum, and they will empty into the vena cava, and then back to the heart. Okay, now we mentioned one process. While this filtrate, this water and dissolved substance, is traveling through this tubular system, we have two processes that occur. One is tubular reabsorption. And again, that is to reabsorb materials back into the blood. All right, tubular reabsorption. And